Hello, this is Barry Nirmal. Please subscribe to my channel by clicking on the subscribe link below. Hello friends, understanding the earth motion around the sun is very important. It is not as simple as I had thought. For too long, the Catholic Church believed that the earth did not move and was the center of the universe. The church thought of Galileo as a heretic, but this did not stop him from writing letters to explain his theory. The Roman Inquisition found these letters and they tried Galileo in 1633, found him, quote, vehemently suspect of heresy, unquote, and sentenced him to house arrest where he remained until his death in 1642. But now religion has become quiet. Even in Islamic countries where people are so backward in thinking, people read science and want to become scientists and engineers. In this video, I try to explain all aspects of Earth's motion around the sun. Scientists have asserted that three factors caused by geometry of Earth's orbit around the sun and the gravitational pull of sun and the neighboring planets causes a noticeable change in climate, temperature, and seasons. This change is cyclical because it repeats itself over time. These three factors are, number one, eccentricity, that is how the earth orbits the sun. Obliquity, which means the angle, what angle does earth face the sun? Okay, because the earth's axis is tilted by about 23.5 degrees. And then the third one is axial precession, that is how earth's axis of rotation changes. We will also discuss apsidal precession, that is how Earth's elliptical path around the sun itself moves. Okay? So let's take number one, orbital eccentricity. The Earth orbits the sun in a slightly elliptical path, which means that there is one point on the path closest to the sun and one point that is farthest away from the sun. Perihelion is when the earth is closest to the sun, about 2 weeks after the December solstice. And aphelion is when the earth is farthest from the sun. It always happens in early July, about 2 weeks after the June solstice. However, the distance of earth from sun does not cause seasons, which are mainly caused by axial tilt of the earth. Now I'm going to show you a diagram which shows aphelion and perihelion and also the distance of earth from the sun. This diagram shows that in winter, the northern hemisphere, that in January, the earth is closer to the sun. The shape of Earth's orbit varies due to the gravitational influence of other planetary objects, particularly the moon. Approximately every 100,000 years, the Earth's orbital path changes from being nearly circular to elliptical. Right now, the Earth's orbit is very nearly circular, not elliptical. The difference of Earth's orbital shape from the perfect circle is known as eccentricity. That is how eccentric its orbit is. An eccentricity value of 0 is the circular orbit, while values between 0 and 1 describe an elliptical orbit. So it starts as a circular orbit like it is now, but like a pendulum, the eccentricity will swing it back the other way with a more elliptical orbit. Because Venus is so close to Earth, its gravitational interactions slightly pull the Earth in its orbit. Then colossal Jupiter also puts Earth slightly outside its orbit opposite end. So Earth periodically goes from a circular orbit to a more elliptical one, that is with high eccentricity. Because of its orbital eccentricity, Earth varies in distance from the Sun. As a result, it receives less solar radiation, causing it to cool. Now, is this timing a coincidence? Due to variations in the eccentricity of the Earth's orbit, the dates when the Earth reaches its perihelion or aphelion are not fixed. In 1246, the December solstice was on the same day as the Earth reached its perihelion. Since then, the perihelion and aphelion dates have differed by a day every 58 years. In the short term, the dates can vary up to 2 days from one year to another. Mathematicians and astronomers estimate that in the year 6430, that is 4,000 years from now, the perihelion will coincide with the March equinox. Now we talk about obliquity, that is how oblique the axis of the Earth is. The next piece of puzzle is obliquity. Right now, Earth's obliquity is 23.5 degrees. That is, the axis on which it revolves or rotates is 23.5 degrees. But over time, it varies from 22.1 to 24.5 and takes 40,000 years to complete a full cycle. Earth's changing obliquity does not alter the total amount of incoming solar radiation. Instead, it affects the geographic distribution of where sunlight hits the Earth. So, if axial tilt increases, winters are colder in both hemispheres. And when the axial tilt decreases, winters are milder in both hemispheres. In summary, more tilt signifies more severe seasons. For instance, this can cause long periods of glaciation. And for Earth as a system, it enters positive and negative climate feedback loops. So remember, at one time, the North American continent was all covered with ice. And then slowly the ice melted. These effects are drastic for long-term climate change. And this is all because of Earth's change and its axial tilt that gradually shifts every 40,000 years. Now we talk about axial precession. Axial precession is the movement of the rotational axis of Earth. This precession has a cycle of roughly 26,000 years. So the position of the sun on the first day of the spring, that is vernal equinox, slowly shifts westward around the sky, which also moves it around our calendar. That is why we refer to the effect as the precession of the equinox. The rate of the shift is 1 day for every 71 years. Precession occurs because the Earth is not a perfect sphere. It flattens out at the poles and widens at the equator. The radius of the Earth at the equator is 6378 kilometers, and at the pole it is 6356 kilometers. Because of this and other asymmetry in the shape of the Earth, gravitational forces from the sun and moon create torque on the axis. Similar to obliquity, the precession does not change the total amount of solar radiation that hits the Earth, but precession primarily alters the perihelion and aphelion. So axial precession is the movement of the rotational axis of Earth. Overall, this increases the seasonal difference from one hemisphere to the other. So Earth's north pole is currently pointing towards distant star Polaris. In the year 14,000, it will point towards the star Vega. If you will be around in the year 14,000, you will be able to verify it with your own eyes. The way medical sciences are advancing, it is quite possible that if not you, your great-grandchild will be around in the year 14,000. So another effect of the Earth's precession is that the star nearest the north celestial pole changes over time. Our familiar North Star today, Polaris, will return to the position of North Star again around 27,800. But due to its own proper motion around the galaxy, it will be farther away from the pole than the 5 degrees it is now. Back in 23,600 BC, it was closer to the pole than it is now. From the start of the building of the Stonehenge monument around 3000 BC, well past the building of the Great Pyramids in Egypt in 2500 BC, a star named Thuban in the constellation Draco would have been perceived as the North Star. Around the Stone Age mammoth hunting time of 12,000 BC, the bright star Vega in the constellation Lyra was the North Star and will be again around the year 14,000 AD. Now let's talk about what causes the weather on Earth. It is not caused by perihelion or aphelion, but is caused by the axial tilt, the tilt of Earth axis. The seasons on Earth are caused by the tilt of the Earth's axis related to the orbit around the Sun. The seasons are not caused by the differences in the distance from the Sun. The Earth is actually closer to the Sun in winter in North Hemisphere and farther away in summer in North Hemisphere. The axis of the Earth's rotation makes an angle of about 23.5 degrees to a line drawn perpendicular to the plane of the orbit. The result is that over the course of a year, the peak height of the Sun in the sky changes. When the Sun is higher in the sky above a region, the light is shining down more directly on the region, that is more intense. The difference in terms of energy concentration can be dramatic. For example, in Bellingham, Washington, the difference in solar energy concentration between the summer and the winter solstice is about 30 degrees. Another factor is the number of daylight hours changing from day to day for any given latitude. For cities in the northern hemisphere, the days are longer in the summer, shorter in the winter. The concentration of sunlight and the length of the daylight hours are the factors creating warmer or colder months. At southern latitudes, that is in the southern hemisphere, the roles are reversed. Longer days and more direct sunlight in the winter, and shorter, less intense sunlight days in the summer. Close to the North Pole, that is above the Arctic Circle, there are days of the year when there is no night at all. As you move just above the Arctic Circle, there is at least one day each summer with no night. The Sun is then always above the horizon and it just makes a 360-degree circuit around you. When you reach the North Pole itself, there are a whole 6 months when the Sun is just above the horizon. That is low energy concentration, but never sets. Likewise, there are 6 months of darkness the rest of the year. The solstice and equinox. For folks living north of the equator, the Sun makes its lowest arc above the sky on the winter solstice, the shortest day of the year. After that day, the Sun follows a higher path across the sky each day and reaches a point when it is in the sky for exactly 12 hours and at night for the other 12. On the equinox, the Sun rises exactly in the east, travels through the sky for 12 hours, and sets exactly in the west. Every place on Earth experiences a 12-hour day and 12-hour night. This happens twice a year, on the vernal, that is spring and autumn equinoxes. After the vernal equinox, that is after the spring equinox, the Sun will continue to follow a higher and higher path through the sky each day, with the days growing longer and longer until it reaches its highest point in the sky on the summer solstice in June, when you have the longest day of the year. heating and cooling the earth. If June 21 is the longest day, the day when we receive the most sunshine, why is it regarded as the beginning of summer and not its peak? Put it another way, why is it August hotter than June in the northern hemisphere? And similarly, why is December 21 the day of least sunshine, the beginning of the winter? And why is February generally colder than December? Consider the surface of the earth, especially the oceans, which heat up and cool down rather slowly. It takes time for the long days to have an effect. In June, the oceans are still somewhat cool from the winter, and that delays the peak heat by about a month and a half. Similarly, in December, the water still holds warmth from the summer, and the coldest days are usually a month and a half or so later. In February, it takes a few weeks for the changing seasons to have an effect on the average temperature of a particular region. Now let's talk about apsidal precession, which means the orbit of the earth rotates gradually over time. The orbits of planets around the sun do not really follow an identical ellipse each time, but actually trace out a flower petal shape because the major axis of each planet's elliptical orbit also precesses within its orbital plane, partly in response to perturbations in the form of the changing gravitational forces exerted by other planets. This is called perihelion precession or apsidal precession. Now watch this video. As the Earth travels around the Sun, its elliptical orbit rotates gradually over time. The eccentricity of its ellipse and the precession rate of the orbits are exaggerated for visualization. Most orbits in the solar system have a much smaller eccentricity and precess at a much slower rate, making them nearly circular and nearly stationary. But in the diagrams and the videos, we exaggerate it so that you can understand it better. Discrepancies between the observed perihelion precession rate of the planet Mercury and that predicted by classical mechanics were prominent among the forms of experimental evidence leading to the acceptance of Einstein's theory of relativity, in particular his general theory of relativity, which accurately predicted the anomalies. Okay, so that's all for today, folks. Thank you very much. Hello. If you have not subscribed to my channel, please do so by clicking on the subscribe link below. Also write your comments in the comment section below. Spread the word. You can share this video with your friends by clicking on the share button below, and you can share it with WhatsApp, with Facebook, Twitter, Instagram, and by sending email to your friends.